The intrinsic safety of standard communication interfaces depends on their design and operational parameters. RS232, which operates at 12 volts, is generally not considered intrinsically safe. Ethernet interfaces can be designed to be intrinsically safe by limiting voltage and current. Certified intrinsically safe Ethernet interfaces are indeed available. RS485 operates at relatively low voltages, typically 5 volts, and is often considered intrinsically safe for hazardous area applications. However, specific devices must be evaluated for intrinsic safety in each unique application. IEC 60079.11, titled Explosive Atmospheres Part 11 Equipment Protection by Intrinsic Safety I, provides detailed guidelines. Communication interfaces should be located in a safe area or within a purged and pressurized enclosure if they are not intrinsically safe. DC low-powered sensors can be intrinsically safe if their design and operating parameters meet certain criteria. For example, sensors operating at low voltage, such as 24 volts, and low current, for example, less than 100 milliamps, can often be considered intrinsically safe. There isn't a universal rule of thumb that applies to all DC devices and communication interfaces, as each device and interface must be individually evaluated for intrinsic safety. If a system or facility includes non-intrinsically safe components, it must be submitted to a listing agency for testing and approval. The listing agency will determine the appropriate hazardous area classification and safety requirements for the system. To ensure compliance with hazardous area regulations and minimize safety risks, it is highly recommended to use certified intrinsically safe components for communication interfaces and other devices within hazardous areas. When assessing the suitability of communication interfaces and devices for use in hazardous areas, understanding the concept of intrinsic safety is crucial. Intrinsic safety, often referred to as is a protection technique applied to electrical equipment and wiring for hazardous locations. The fundamental principle behind intrinsic safety is to limit the energy, both electrical and thermal, available in a circuit to a level below that required to ignite a specific hazardous atmospheric mixture. This approach eliminates the possibility of ignition under both normal operation and fault conditions. To achieve intrinsic safety, several design considerations must be implemented. Firstly, the voltage and current levels within the circuit must be strictly controlled. This is typically accomplished through the use of current-limiting resistors, voltage clamping devices like Zener diodes, and other energy-limiting components. The goal is to ensure that even under worst-case fault scenarios, the available energy remains below the minimum ignition energy, or MI, for the hazardous substance in question. Secondly, the circuit's capacitance and inductance must be carefully managed. Capacitance stores electrical energy, while inductance stores magnetic energy. Both can release their stored energy in the form of a spark if the circuit is disrupted. Therefore, intrinsically safe circuits are designed to minimize capacitance and inductance, often through the use of specially designed components and wiring techniques. Thirdly, segregation and isolation techniques are employed to prevent the transfer of energy from non-intrinsically safe circuits to intrinsically safe circuits. This can involve physical separation, shielding, and the use of intrinsically safe barriers, which are devices that limit voltage and current to safe levels. Communication interfaces like RS232, RS485, and Ethernet pose unique challenges in hazardous areas. RS232, while widely used, typically operates at voltage levels that exceed the limits for intrinsic safety. The 12-volt signaling levels commonly used in RS232 can generate sparks with sufficient energy to ignite flammable substances. Therefore, standard RS232 interfaces are generally not considered intrinsically safe and require alternative protection methods such as explosion-proof enclosures or purging and pressurization systems when used in hazardous locations. RS485, on the other hand, operates at low voltage levels, typically 5 volts, making it more amenable to intrinsic safety design. However, even at these low voltages, careful consideration must be given to current limiting and capacitance/inductance management to ensure that the circuit remains intrinsically safe under all operating conditions. Ethernet interfaces present a more complex scenario. Standard Ethernet operates at relatively high data rates and voltage levels, which can make it difficult to achieve intrinsic safety. However, specialized intrinsically safe Ethernet interfaces are available. These interfaces employ various techniques, such as current limiting, voltage clamping, and signal isolation to reduce the risk of ignition. In some cases, intrinsically safe Ethernet interfaces may utilize fiber optic cabling, which eliminates the risk of electrical sparking altogether. When evaluating DC low-powered sensors for use in hazardous areas, it's essential to consider their operating voltage, current, and power consumption. Sensors that operate at low voltage, for instance 24 volts or less, and draw minimal current, typically less than 100 milliamps, are more likely to be suitable for intrinsically safe applications. However, it's still crucial to verify that the sensor's design incorporates appropriate energy-limiting features and that it has been certified by a recognized testing laboratory. There is no universal rule of thumb that guarantees the intrinsic safety of all DC devices and communication interfaces. Each device and interface must be individually assessed based on its specific design and operating parameters. Factors such as voltage, current, power, capacitance, inductance, and operating temperature all play a role in determining the overall safety of the device. To ensure compliance with hazardous area regulations and minimize safety risks, it is strongly recommended to use certified intrinsically safe components for all communication interfaces and devices located within hazardous areas. Certification by a recognized testing laboratory, such as Underwriters Laboratories, or the Canadian Standards Association, or CSA, provides assurance that the device has been rigorously tested and meets the applicable safety standard. When a system or facility incorporates non-intrinsically safe components, it is necessary to submit the entire system to a listing agency for testing and approval. The listing agency will conduct a comprehensive evaluation to determine the appropriate hazardous area classification and safety requirements for the system. This evaluation may involve a combination of testing, analysis, and inspection to ensure that the system as a whole meets the required safety standards. The specific requirements for hazardous area installations are typically outlined in national and international standards such as the National Electrical Code, or NEC, in the United States and IEC 60079 internationally. These standards provide detailed guidance on equipment selection, installation practices, and maintenance procedures for hazardous locations. Understanding the different hazardous area classifications is essential for selecting the appropriate equipment and protection methods. Hazardous areas are typically classified based on the type of hazardous substance present, the likelihood of its presence, and the potential for ignition. For example, Class I locations involve flammable gases or vapors, Class Roman II locations involve combustible dust, and Class Roman III locations involve ignitable fibers or flyings. Within each class, divisions or zones further categorize the risk level. Division 1 or Zone 0 locations represent the highest risk, where the hazardous substance is present continuously or for long periods. Division 2 or Zone 1 locations represent a moderate risk, where the hazardous substance is likely to be present under normal operating conditions. Zone 2 locations represent the lowest risk, where the hazardous substance is only likely to be present under abnormal conditions. The selection of equipment for hazardous areas must be based on the specific classification of the location. Equipment must be designed and certified for use in the specific class, division, or zone in which it will be installed. This ensures that the equipment will not create an ignition source under normal or fault conditions. In addition to intrinsic safety, other protection methods are commonly used in hazardous areas. These methods include explosion-proof enclosures, purging and pressurization systems, and oil immersion. Explosion-proof enclosures are designed to contain any internal explosion without allowing it to propagate to the surrounding atmosphere. Purging and pressurization systems use a positive pressure of clean air or inert gas to prevent the entry of hazardous substances into an enclosure. Oil immersion involves submerging electrical equipment in oil to prevent ignition of flammable substances. The selection of the appropriate protection method depends on various factors, including the type of hazardous substance present, the risk level, and the size and complexity of the equipment. In many cases, a combination of protection methods may be required to achieve the desired level of safety. Proper installation and maintenance practices are crucial for ensuring the continued safety of electrical equipment in hazardous areas. Installation must be performed by qualified personnel who are familiar with the applicable codes and standards. Wiring must be properly sealed to prevent the ingress of hazardous substances. Equipment must be regularly inspected and maintained to ensure that it is in good working order. Any damaged or malfunctioning equipment must be promptly repaired or replaced. In conclusion, the use of communication interfaces and DC devices in hazardous areas requires careful consideration of intrinsic safety principles and compliance with applicable regulations. While standard communication interfaces like RS232 are generally not intrinsically safe, specialized intrinsically safe versions of Ethernet and RS485 are available. DC low-powered sensors can be intrinsically safe if they are designed with appropriate energy-limiting features. However, each device and interface must be individually assessed to ensure its suitability for the specific hazardous area in which it will be used. The use of certified intrinsically safe components and adherence to proper installation and maintenance practices are essential for minimizing safety risks and ensuring compliance with hazardous area regulations. It is important to reiterate that there is no single rule of thumb for determining whether a device or communication interface is intrinsically safe. Each device must be evaluated individually by a qualified expert who understands the principles of intrinsic safety and the requirements of the relevant standards. This evaluation should consider all aspects of the device's design and operation, including its voltage, current, power, capacitance, inductance, and operating temperature. The expert should also consider the specific hazardous atmosphere in which the device will be used, including the type of hazardous substance present, its concentration, and its ignition characteristics. Based on this evaluation, the expert can determine whether the device meets the requirements for intrinsic safety and can be safely used in a hazardous area. In addition to individual device evaluation, it is also important to consider the overall system in which the device will be used. The system should be designed to minimize the risk of ignition and to prevent the propagation of explosions. This may involve the use of intrinsically safe barriers, explosion-proof enclosures, purging and pressurization systems, and other protection methods. The system should also be properly grounded and bonded to prevent the buildup of static electricity, which can be a source of ignition in hazardous areas. Regular inspections and maintenance are essential for ensuring the continued safety of electrical equipment in hazardous areas. These inspections should be performed by qualified personnel who are familiar with the applicable codes and standards. The inspection should include a visual examination of the equipment, as well as electrical testing to verify that it is functioning properly. Any damaged or malfunctioning equipment should be promptly repaired or replaced. It is also important to keep accurate records of all inspections and maintenance activities. These records can be used to track the performance of the equipment and to identify potential problems before they become serious. In addition to following the specific requirements of the applicable codes and standards, it is also important to exercise good engineering judgment when designing and installing electrical equipment in hazardous areas. This means taking a conservative approach and erring on the side of safety. If there is any doubt about the safety of a particular device or installation, it is best to consult with a qualified expert before proceeding. By following these guidelines, it is possible to safely use communication interfaces and DC devices in hazardous areas. However, it is important to remember that there is no such thing as absolute safety. There is always some risk involved in working with electrical equipment in hazardous areas. Therefore, it is important to take all necessary precautions and to be constantly vigilant to prevent accidents. Intrinsic safety relies on limiting the energy in electrical circuits to prevent ignition. RS232 at 12 volts is typically not intrinsically safe. Ethernet can be intrinsically safe if designed with voltage and current limits. RS485 often operates at low voltages 5 volts and can be intrinsically safe. IEC 60079.11 is the standard for intrinsic safety. Locate non-intrinsically safe interfaces in safe areas or purged enclosures. Low-power DC sensors can be intrinsically safe if voltage G 24 volts and current G 100 milliamps are low. There's no universal rule of thumb. Evaluate each device individually. Submit non-intrinsically safe systems for listing and testing. Use certified intrinsically safe components for safety.